All right, section 6.4 is called logarithmic functions, and how we start with logarithmic functions is we start off here with the exponential function. Why is this called an exponential function? Because the variable is in the exponent position. So I'm going to make a graph of this real quick, like we did with 3 to the x power. This is 2 to the x power, so 0 would be 1. Anything to the 0 power is 1, except for 0, of course. 0 to the 0 power is undefined. And we have 1 would be 2, negative 1 would be a half because it flips it upside down. So this is the graph for this. It's going to go through here. 1, 2 would be like there, 1.5, so it looks like so. Okay, just a quick sketch of it. Now, this is a one-to-one function. What's important about the fact that this is a one-to-one function is the fact that when you do the inverse of it, the inverse is also a function. The inverse of any one-to-one function is also a function. So how do you find the inverse? You switch x and y, solve for y. Switch x and y, solve for y. Okay, I switched x and y. Well, crap, how do I solve for y? How do I get y by itself? So mathematicians invented a way to get y by itself. And that is the relationship between these three things here, and the logarithm is how we relate these three things. So we do log base 2, that's the base, of x is equal to the exponent y. So logarithms are the mathematics of exponents. The exponent is always what comes out of a log function. So it's measuring exponents. So it's not going to grow very fast because the exponents don't change that fast. Like you go from powers of the hundreds place is 10 to the second power, the thousands place is 10 to the thirds power. You only go from 1 or 2 to 3. You're not like going huge amounts. So it doesn't grow very fast, and you can see that in the graph here. The inverse of this would be switching these around. So it'd be 1, 0, 2, 1, and a half, negative 1. So a half over negative 1 would be like here, and then 1, 0 would be like here, and then 2, 1 would be like here, so it grows like this. They both grow, but how they grow is different. This one increases at an increasing rate, this one increases at a decreasing rate. So that's why we did all this talk about inverses, because exponential functions need an inverse to solve them, and that inverse is log functions. So logs are the opposite of exponential. Like addition has subtraction, multiplication has division, exponents have logs. That's how we solve a log equation, is using, or an exponent equation is using logs. Okay, so there's a relationship here that's important. 10 to the second power is 100. We know that. So this is how we get log base 10 of 100 is equal to 2. So the base is 10. The exponent goes here, and the answer goes right here. So this is the base, this is the answer, and this is the exponent. So that's how we read this. So years ago, one of my students was like, oh, logarithms are bay before anyone else. So you don't need a significant other in your life. All you need is a logarithm, because logarithms are your bay before anyone else. All right, so here are the examples. We're going to write these in log form first. So I'm going to say log. The base is 3, and 4.6 is the answer, and then x is the exponent. So the exponent goes there, the base goes there, the answer goes there. And that's writing it in log form. The next example asks us to write it in exponent form. So now we're going to go the other direction. So the base is 2, that's the exponent, right? Squared is equal to answer 4. So there it's in exponent form, log form, being able to switch between the two. Okay, so this is pretty significant here, right? Let me get these on the screen here. So exponent form switching to log form switching to exponent form, log form going to exponent, exponent going back to log. So that's really important, because that'll get you in and out of trouble when you're trying to figure problems out. You're like, I don't know how to do this. Well, switch the form that it's in, and maybe it'll make sense. All right, so that's what we're going to do here. We're like, I don't know, log base 1/3 of 9 is equal to, well, I don't know. So let's go ahead and let's go ahead and rearrange it. So it'd be 1/3 to the x power is equal to 9. So how do we do this? Well, if I do 3 squared would be 9, but it's flipped. It needs to be flipped upside down. So 2 would make it 9, but if you flip it upside down with that negative exponent, so x is -2. So 1/3 to the -2 is 9. You could type that into the calculator and prove to yourself that it really is 9. So I'll do that right now. So we got clear, and we 1/3. So we got 1 divided by 3. There's 1/3 to the power of -2. You can see that pretty well, and the answer will be 9. So it really does work. Just to prove to you that logarithms are the mathematics of exponents, if I do log of 7,845, I kind of know the answer to this already, because that's the ones place, the tens place, the hundreds place, and the thousands place. The thousands place is 10 to the third power. So because that's the thousands place, it's really just counting the exponent of 3, like 10 to the third power is 1,000, and it's 7,000. So the answer is going to be 3 point something. I already know that. And log on the calculator is base 10. So if I do 10 to the power of the last answer, A&S copies and pastes that in there, it'll be back to the original 7845. So logarithms are keeping track of the exponents. So for example, if I have log of 1, 2, 3, the answer for that is going to be 2 something, because it's the hundreds place is the largest place value. So it's going to be 2.0 blah, blah, blah. And so if you do a 4-digit number, the answer is going to be 3 something. If we did a 5-digit number, right? So 5-digit number, so we do log of bum, 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 bum. That's a 5-digit number. And so that's tens, hundreds, or sorry, ones, tens, hundreds, thousands. 10 thousands is 10 to the 4th power. So when we do log of this number, it's keeping track of that exponent, the fact that it's in the 10,000s place. It's actually 50,000, and the answer is going to be 4 something. And then 10 to the power of that second answer will take us back to the 56,487. All right, last 2 examples. So I'm going to rearrange this and solve for x. So base is 3, exponent is 2, and that's 3x minus 2. Now this is simple algebra from here. This is 9, and then 3x minus 2. Add the 2 over, 11 is equal to 3x, divide, 11/3 is equal to x. So that's the answer for that one. So you just rearrange it, base, exponent, answer, blah, blah, blah. Okay, last example has e in it. E is the Euler number. E is approximately equal to 2.718 and change. It never stops, it never repeats. I'll put a video up about E so you can know what E is. So here I'm going to clean this up first before I switch it. So I'm going to divide both sides by 4, get e to the x plus 1. That doesn't divide evenly, but it gives me a really nice decimal, so I'm going to go ahead and use the decimal. Normally I don't use decimals, but since it's such a nice one, I'll go ahead and do that. Now I'm going to rearrange this. I'm going to rearrange it with log. Log base e of answer 125 is equal to the exponent x plus 1, right? There's your base, there's your answer, right? And then the exponent. Now log base e, the definition of that, if you remember this from the past, log base e of x is natural log of x. So log base e is a special log, and we call that natural log. So this is the natural log of 1.25 is equal to x minus 1, plus 1, plus 1. Subtract the 1 over, I was getting ahead of myself, and then minus 1 is equal to x. So that's the answer for this. I'm going to put some parentheses there, so it's natural log of this number minus 1 is equal to x. That makes it even more clear to the answer. All right, that pretty much does it for this, and sorry about getting this video out late, but it is what it is.